So we're going to start working with logarithmic functions. And when we have a logarithmic function, we have two forms of that function. We can either write it in logarithmic form, which we see in 1 through 6 on the worksheet, or we can write it in exponential form, which I have the form of that written over here off to the side. So these are your frameworks for these forms. And we can go back and forth between these two forms. So that's what we're going to practice first. On 1 through 6, we're going to look at rewriting the equation into exponential form. So it's in logarithmic form right now. We're going to rewrite it into exponential form. So if I take number 1, and I'm just going to rewrite number 1 underneath my form over here. So number 1 says log base 7 of 49, that's how we read that, equals 2. So the log with a base of 7 of 49 equals 2. And if you can see, if we take those same numbers, the same values that are lining up with each of those variables, and we put it down here into exponential form. So up here we see that our b is 7, we see that our x is 2, and we see that our y is 49. So 7 squared equals 49 is the same thing as this original equation they gave us. We just changed forms. So the top one, the one given, is in logarithmic form. We changed it into exponential form. All right, I'm going to do the same thing with number 2. So we have log base 2 of 16 equals 4. If I come down here to my exponential form, I can see that my base is 2, my x is 4, my y is 16. So rewritten in exponential form is 2 to the 4th equals 16. This is the same thing as the logarithmic function that was given to us. Right, and we'll do the same thing with number 3. Log base 5 of 125 equals 3. Come down here, we identify our b as 5, our x as 3, and our y is 125. So 5 cubed equals 125 is the same equation as the log base 5 of 125 equals 3. All right, so we're just writing them into a different form, and we can go backward and go into logarithmic form as well. Now in 789, they want us to evaluate those logarithms without using a calculator. So what we're looking for in number 7 is we were going to have a base of 9. I'm looking for the exponent. I'm looking for my x that when all said and done is going to give me 81. They really could have had this log base 9 of 81 and they could have said it equals x, and we're solving for x. And then you can see it follows the same form that we just did over here, going from logarithmic form to exponential form. So from here I can easily see that x needs to be 2 in order to have this equation work out. So 9 squared would give me an answer of 81. Okay, so my answer here is 2. If I do the same thing on number 8, then I have a base of 8. I'm looking for an exponent. Then when I raise 8 to that exponent, I'm going to get 1. We know that the only exponent that we can raise anything to and get 1 is going to be 0. So my answer here is 0. And then on number 9, my base is 3. I'm going to raise it to some exponent, and when I do that, I want to get 1/3. So if we think about the only difference between 3 and 1/3 is that they're reciprocals of each other. So if we made x -1, then that would require us to reciprocate that 3 into the denominator, and we would end up with 1/3. So here our x is -1. So now we can figure out some of these with a calculator. And so 13 through 15, we'll use a calculator. And usually when we find the logarithm, we round it to the nearest 3 decimal places. So we'll round to the thousandth place when we find these logarithms. Uh, 13, that ln means natural logarithm. And what that is referring to is a logarithm that has a base of e. So that was Euler's number that we talked about in the last lesson. It has the value of 2.71 and keeps going. That's what that ln stands for. On your calculator, it's right here. And so you'll just click ln. It's going to pull up that open parentheses. And then you can go to your second key, get the square root symbol, and then put your 5 in. And then hit enter. And you should come up with 0.8047. We're going to round it to 0.805. So 3 decimal places. All right, and then you can clear that out. When it just says log, like in 14, we're talking about a common log, which is going to have a base of 10. We don't have to do anything with that though, because we're using the calculator. You're just going to hit log, hit your 110, enter, and again, that'll be rounded to the thousandth place, so 2.041. And then on that last one, we have another natural logarithm. So again, the base would be e on this. 1 divided by 2. And you'll get negative 0.693. All right, so with these logarithmic functions, just like in all of the other functions that we've done, you can find the inverse of the function by swapping the x and the y variables. So if we were to do that on number 16, that would look like this for your first line. So this is not tricky at all. We're just keeping everything the same except swapping x and y. The tricky part comes because now we have to solve for y, and we're using these logarithmic functions to do that. I'm going to actually switch this and put the x on the other side just so it looks a little bit more like the logarithmic functions at the top of the page did. So now we're talking about going into our exponential notation from now. So we're going to take this into exponential form in order to solve for y. So in order to do that, we're going to drop that log, right? We're going to write 5 to the x equals our y. All right, and I'm getting that, once again, let me write out our base formulas here. So these are the ones that I had written at the top of the page. Here's your logarithmic form, which is what we see here on the second line. We want to take it to our exponential form, which looks like this. So if 5 is our base, our b, in logarithmic form, then it's going to become b here in our exponential form. All right, so this is our 2 different forms. This is log form, and this is exponential form. And now you can see that just by changing it into exponential form, we solved for y. The log goes away and we have it in exponential form. We can leave it like this, or in the book, you're more likely actually to see it written in with F inverse form. So we could write it like that as well. They mean the same thing. I'm just changing the notation on the y, calling it F inverse x. And let's actually do 18 before we do 17. So on 18, we have y equals log 1/5 x. We're going to swap our x and our y. And then I'm actually going to rewrite that. And when I do that, I'm going to put the x on the other side, just so it looks a little bit more like this form up here. All right, so I can look up at my form. I'm in logarithmic form. I can identify my b in this problem as 1/5. So I'm going to write that. And then I can see from my exponential form that I want to raise that b to the x power. And then that is going to equal y. So there it is in exponential form. If I write it in inverse form, it would look like this, f inverse x. But again, they're both saying the same thing. I'm going to come up here on the worksheet and do number 17 right here. So in this problem, once again, even though it has the ln there, the natural log, we're still going to switch our x and our y. That hasn't changed. And so the natural log, when you see the natural log, it always means the base is going to be e. So when you see ln, it means the base is e, and e is Euler's number that we talked about before. All right, so when we see that ln, and if I come over here to my logarithmic form, I can see that, I'm looking for log base b, but I don't have it over here. Let me go ahead and swap this again. I'm just swapping sides. So when I see ln, what I need to say to myself is they're referring to Euler's number, they're referring to e. So I'm going to write that down. That's going to be my base. So that this is b in this case, and it's going to line up with my b in my exponential form as well. All right, I'm going to raise it to my x over here, and then that's going to equal this y right there. All right, so again, that is correct. If I write it as with inverse notation, it would look like this. Again, both of them are saying the same thing. I've just changed the notation on the right-hand side of the equation. Now, in order to graph a function in logarithmic form, we have to change it to exponential form. So on 22, we're going to work to change that log base 3x to exponential form. I'm going to call f of x y, and I'm actually going to put that on the other side just again so that it matches our form, our base form a little bit better. So again, that form is log base b of y equals x. So if I come over here, I can see, in my x, and then let me write our exponential form out here as well again. So again, log form, exponential form. Okay. So I'm going to go from log form to exponential form. I can see here that my b is 3. And I'm going to raise that to the y, because that's actually that is what my my x corresponds to in this equation. I know that's probably a little bit confusing, but that this y is what we're saying the whole thing equals. And so that is actually our exponent. Remember, these are just letters. We could pick any letter to represent these variables. So it just so happens that these now are reversed from what our basic form looks like over here. And that's going to equal x. So we have it solved for exponential and into our exponential form, and now we're going to make an xy table. And we're going to need to kind of think of this backwards a little bit. If we want x to equal 1, so that would be right here, our x to equal 1, we know our y would have to be 0. So 3 to the 0 power equals 1. If we want, let's do the next easy thing, would be if we wanted our x to be 3, then we know y needs to be 1. You don't necessarily have to work backwards like that, but you do need to just keep in mind that you're plugging in your exponent is your dependent variable in this function. So if you wanted to go ahead and say 3 raised to the 0 power, put 0 in your in the table for y. Just make sure you don't do that backwards, and then you can say 3 to the 0 power is going to give me an x of 1. So you don't necessarily have to go backwards the way I just did, but and then we'll plot those 1, 0, 3 and 1. And in the logarithmic functions, we're actually going to have vertical asymptotes. So instead of horizontal asymptotes, which we saw in our exponential functions at the beginning of the chapter, now we're going to have vertical asymptotes. Up here, you can see that our x isn't being shifted at all. We don't have any shifting going on in this problem. If we wanted to write it in, we would say we had an x of 0, x plus 0. So that means that we're not shifting in any way. Instead of it being the x-axis is the asymptote, though, because we have vertical for logarithms, we have an x of 0 for this one. So what that means is that it's going to approach this asymptote, but not touch it or cross it. So that's how these exponential functions are, these logarithmic functions are slightly different from our exponentials. All right, so from there, if we identify our domain is going to be limited here because we're not crossing over that y-axis. So all of our x's have to be greater than 0. And now our range, though, you can see our range is going to be all reals. This is going to extend upward forever and downward as well. And so eventually it has the potential to run through all those y's. Okay, so this is actually the opposite of what we would see on our domain and range for our exponentials. So right away on number 23, you can see we're going to have some horizontal movement because we've got an x plus 2. That's really a minus a negative 2. So we're going to be shifting this to the left 2 units, which is going to make our asymptote right here at x equals negative 2. Again, it's going to be a vertical asymptote. So our line is going to approach that, but not cross it or touch it. We need to rewrite this into exponential form. So I'm going to write it down here. I'm going to make it equal to y instead of f of x, and I'm putting that y on the other side just so that it matches our logarithmic pattern right here. All right, so my base is 3. So I'm going to write that. My x, the thing that this all equals, in this case is y, again, just like the previous problem. And it's going to equal the y in the problem. So in the pattern right here, my y is this x plus 2. So this should read 3 to the y equals x plus 2. All right, and then I'm just going to bring that 2 over to the other side, and then we can make a table. Okay, and if I put a y of 0 in right here, so I'm going to write that in the table under y. That's going to raise my 3 to the 0 power. That's 1. 1 take away 2 is going to give me an x of negative 1. If I make my y 1, 3 raised to the first power is 3. Take away 2 is going to give me an x of 1. So I'm going to plug those in. Negative 1, 0. 1, 1. Keeping in mind that I'm going to run this close to that asymptote but not cross it. My domain here, again, I can't go past that x of negative 2. So that's going to be, x has to be greater than negative 2. And then my range, again, will be all reals for the same reason that I described in number 22.